Good morning, everyone. Today we're going to study about dental ceramics. The contents for the presentation will be introduction, definition, difference between ceramics and porcelain, terminologies, historical perspective of ceramics, composition, classification of ceramics, properties of dental ceramics, fabrication of dental ceramic restoration, methods of strengthening ceramics. So first, let us know what ceramic material is. They are inorganic compounds formed of metallic or semi-metallic and non-metallic elements, which are subjected to high heat treatment for a time period to achieve desirable properties. So, where can we use ceramic? For denture teeth, jacket crowns, porcelain fused to metal crowns and bridgework, all ceramic bridgeworks, veneers, onlays, inlays, and implants. So ceramic, an earthy material, usually of silicate nature, and may be defined as a combination of one or more metals with a non-metallic element, usually oxygen. Dental ceramic, an inorganic compound with non-metallic properties, typically consisting of oxygen and one or more metallic or semi-metallic elements like aluminum, calcium, lithium, magnesium, potassium, silicon, sodium, tin, titanium, and zirconium, that is formulated to produce the whole or a part of ceramic-based processes. Now, let us understand the difference between ceramic and porcelain. So ceramic, it's mainly non-metallic, inorganic, man-made solid objects formed by baking raw materials at high temperatures. And what is porcelain? It's a family of ceramic materials composed essentially of kaolin, quartz, feldspar fired at high temperature. Now, dental porcelain, a ceramic produced by sintering a mixture of feldspar, silica, alumina, other metal oxides, pigments, and opacifying agents. Except for porcelain denture teeth, dental porcelain is not made from kaolin. Now, the general composition of ceramic, it has two phases, vitreous phase and crystalline phase. Vitreous phase is also glassy phase. It is a phase which is responsible for aesthetics only. It is formed by vitrification where the molten glass has been cooled without crystallization. It is amorphous in structure. Now, crystalline phase, it is the phase which is responsible for strength and hardness only. It is formed by devitrification where the crystallization of the glass occurs at high temperature in the presence of nucleating agents. It is crystalline in structure. So, vitreous phase is basically formed by vitrification and crystalline phase is basically formed by devitrification. And glassy phase or vitreous phase is mainly for aesthetics, and crystalline phase is responsible for strength and hardness. Now, composition. So, ceramic material consists of various components: feldspar, kaolin, quartz, alumina, different oxides of metals, pigments. So, feldspar consists of 60 to 80%. So basic glass former is feldspar. Then kaolin 3 to 5%, that is binder. Quartz is a filler, 15 to 25%. Alumina is a glass former, 88 to 20%. Boric oxide is mainly for fluxes that we use, so 2 to 7%. In oxides of sodium, potassium, calcium, 9 to 15%. These are also fluxes or glass modifiers. And metallic pigments less than 1% for color matching in pigments. So this is the composition. Next, now we will study about individual components of ceramics. So first is feldspar, that we already seen it is 60 to 80%. It is naturally occurring double silicate of potassium and aluminum. Natural feldspars can be either sodium feldspar or potassium feldspar. For dental purposes, light potassium-based feldspar is generally selected because of its increased resistance to pyroclastic flow and increased viscosity. So generally, we use potassium-based feldspar in our practice. Next is the properties of feldspar. So first, resistant to pyroclastic flow, that is less rounding, loss of tooth form, and obliteration of surface marking. Then between 1150 degrees Celsius to 1530 degrees Celsius, it undergoes incongruent melting to form lucite. Lucite is a crystalline potassium aluminum silicate mineral. It is a strengthening material used in metal ceramic restorations, all ceramic and glass ceramic materials like IPS, amorphous, and optic. The functions of feldspar: it is basic glass former, lowest fusing component during firing, and acts as a matrix. It acts as a flux and surface glaze. Next is kaolin. Kaolin is basically binder. It's present in 3 to 5%. It is a white clay-like material which is hydrated aluminum silicate. Functions are: it acts as a binder. On heating, it reacts limitedly with feldspar and thereby provides rigidity. It gives opacity to the mass. Then disadvantages: it is white in color and hence reduces the translucency of porcelain. Next, quartz or silica. These polymorphic forms such as crystalline quartz, cristobalite, and tridamide, and amorphous fused quartz. Silica in porcelain is obtained by grinding floor quartz. Functions: it acts as a refractory skeleton. It provides strength and hardness to porcelain during fusing. It remains unchanged at the usual firing temperatures and hence contributes to the stability of the mass during heating. Then aluminum oxide, it's present in 8 to 20%. Functions: it gives strength and opacity to the porcelain. It increases the viscosity of porcelain during firing. Then fluxes, they are present in 9 to 15%, and examples are sodium carbonate, lithium carbonate, and low fusing glasses. Function: lower the sintering temperature increases the flow of porcelain. They also absorb and remove impurities. Next, pigments. Prepared by fusing different metallic oxides together with glass and feldspar. So we have titanium oxide that gives yellowish brown pigment, then manganese oxide that gives lavender appearance, then cobalt oxide bluish, then ferric oxide platinum grayish, chromium oxide copper oxide greenish, ferrous oxide nickel oxide brownish, then chromium tin, chromium alumina pinkish, indium yellow or ivory, and uranium oxide a lanthanide fluorescence appearance. So these are the pigments that we use for different color shades. Then opacifiers generally consist of metallic oxides, that is between 8% to 15%, down to a very fine particle size which is less than 5 microns, to prevent a speckled appearance in porcelain, to give fine appearance. Then opacifiers can be cerium oxide, zirconium oxide, titanium oxide, tin oxide. Then to understand ceramic, we need to understand different terminologies. So first is alumina core. The substructure or the framework for crown or bridge that is made up of aluminum oxide. So this is basically alumina core. Next is CAD/CAM ceramic, a partially or fully sintered ceramic blank that is used to produce a dental core or veneer structure using a computer-aided design and computer-aided manufacturing or milling process. Then comes sintering. Process of heating closely packed particles below their melting temperature to promote atomic diffusion across particle boundaries and densification of the mass. So that is sintering. Next comes castable ceramic, a glass specially formulated to be cast into a mold and converted by heating to a glass ceramic as a core coping or framework for the ceramic processes. Then comes ceramic frets. It's a powdered ceramic material fired in a dental lab to produce a dental porcelain veneer layer over a core material. Frets may be glass or a mixture of glass and crystalline particles, which commonly contain inorganic pigments. Then ceramic glaze, fine glass particles or powder that can be fired on a dental ceramic core or dental porcelain to form a smooth glassy surface. That is ceramic glaze. Now coming to ceramic pressable. Ceramic with a high glass content that can be heated to a temperature and forced to flow under uniaxial pressure to fill a cavity in refractory mold. So that is ceramic pressable. Then comes ceramic stain. A fine glass powder containing one or more pigments, that's colored metal oxides, that is applied superficially to a ceramic restoration to give different color appearance. So that is ceramic stain. Then comes copy milling. Process of cutting or grinding a structure using a device that traces the surface of a master pattern, similar to a key cutting procedure in 3 dimensions. Then comes glass ceramic. A ceramic that is formed to shape in a glassy state and subsequently heat treated to partially or completely crystallize the object. Glass ceramic blanks are also available for CAD/CAM processes. Then comes glass infiltrated ceramic. A crystalline core ceramic whose interconnected pore network is infiltrated during heating by capillary inflow of a low viscosity, highly wetting glass. These infiltrated core materials are veneered with porcelain, alumina, magnesia, alumina spinel, or alumina zirconia core ceramics can be used for this process. Then comes green state, the semi-hard, pre-fired condition of a ceramic object. A green ceramic may be wet, as produced by slip casting, or it may be isostatically pressed to a shape prior to firing. Green ceramics are always porous. They are too fragile for use intraorally. Then, slip casting. Process of forming ceramic shapes by applying an aqueous slurry of ceramic particles to a porous substrate and removing the water by capillary action. This densifies the deposited ceramic powder into a green body, which is subsequently sintered to achieve higher density and strength. Then comes porcelain opaque. A fine dental porcelain provides either as a paste or powder that is used to mask the cover of a metal substructure or ceramic core for fixed processes. Porcelain body. A dental porcelain used to create the anatomy and shape of a fixed prosthesis. Then porcelain incisor. A dental porcelain used to create the anatomy and incisor portion. These porcelains are generally more translucent than opaque and gingival porcelains. Then porcelain shoulder. A dental porcelain that is used to build up the cervical area of a metal ceramic crown to produce an aesthetic butt joint margin. Next. This porcelain is usually more opaque than body or incisal porcelain. This porcelain also has a higher sintering temperature than the adjacent body porcelain, so as to retain the sharp edge at the margin during subsequent sintering process. Next, porcelain aluminous. A dental porcelain whose thermal expansion coefficient is suitable for use as a veneer over an alumina core. This porcelain creates the anatomy of the crown and improves the aesthetics of alumina-based processes. Then comes porcelain feldspathic, a specially formulated dental porcelain that contains leucite crystals, that is potassium aluminum silicate, in a glass matrix that is used for veneering the metal framework of metal ceramic prostheses. Leucite crystals have high thermal expansion, which makes the porcelain thermally compatible with high expansion noble and nickel-based alloys. Then we have spinel, a porous slip cast ceramic that is composed of magnesium and aluminate. That is glass infiltrated to produce a core ceramic. Then comes zirconia, a partially stabilized zirconium oxide, usually in the tetragonal phase, that is used primarily as a core for dental processes. It has been introduced as a monolithic ceramic to be used without a veneering ceramic. Now we have zirconia core, a partially stabilized tetragonal zirconia that is used for producing the core, veneered framework or substructure for crowns or bridges. Then what we have is classification. According to the use or indications, and according to composition, according to the processing method, according to firing temperature, according to the microstructure, according to the technology. So first is according to the indications. So it is basically based on where and how are we using ceramics. So first, if you're using in anteriors or posteriors as a crown or as veneers for postal cores or for FPDs or for stained ceramic or for glazed ceramic. Then we have according to composition. So composition is basically first is all ceramic and second is PFM, that is porcelain fused to metals. So In traditional dental ceramics, we have silica-based ceramic. In glass ceramics, we have leucide reinforced feldspathic ceramics, floor mica glass ceramics, lithium disilicate. In high-strength core ceramic, we have glass infiltrated ceramic, metal oxide ceramics. In metal oxide, we have two, alumina and zirconia-based ceramics. So basically, this is on the basis of composition. Okay. Next, according to the processing method, that is, first is it can be sintering, partial sintering, glass infiltration, CAD cam, or copper milling. According to firing temperatures, it can be ultra low fusing, low fusing. So in ultra low fusing, it is less than 850 degrees Celsius. In low fusing, it is 850 to 1100 degrees Celsius. And in medium fusing, it is between 1100 to 1300 degrees Celsius. And high fusing, it is greater than 1300 degrees Celsius. Then according to microstructure, glass, crystalline, and crystal containing glass. And according to the translucency, opaque, translucent, and transparent. In conventional powder or slurry technique. Now we are going to discuss the different techniques. So first is conventional powder or slurry technique. It is a traditional method of forming ceramic processes and consists of following steps: compounding, packing, preheating, sintering, surface treatment, and post-clean cooling. So first is compounding. Compounding is basically mixing. Next come packing or condensation. The process of bringing the particles closer and of removing the liquid binder is known as condensation. Dense packing has following benefits. It improves substructure of porcelain and dispenses trapped air, so it results in less porosity. Then we have increased density, less shrinkage during firing, and enhanced surface structure and strength. Next is preheating or drying. So porcelain, placing the porcelain object on a tray in front of a preheated furnace at 60 degrees Celsius for 5 minutes for low fusing porcelain at 480 degrees Celsius for 8 minutes for high fusing porcelains. The significance of preheating stage. Removal of excess water, allowing the porcelain object to gain its green strength, then preventing sudden production of steam that could result in voids or fractures. Then ceramic particles held together in the green state after all the liquid has been dried off. Next comes sintering or firing temperature. So mechanism of sintering, also mechanism of firing. First is initial firing temperature. The voids are occupied by the atmosphere of the furnace. As the sintering of the particles begins, the porcelain particles bond at their points of contact. As the temperature rises, the sintered glass gradually flows to fill up the air spaces. The particles fuse together by sintering, forming a continuous mass. This results in a decrease in the volume referred to as firing shrinkage. Next, with progression of firing, the gaps between the particles become porosities. The viscosity of the glass is low enough for it to flow due to its own surface tension. The result is that the porosity voids will gradually become rounded as firing proceeds. The final firing stage. The voids slowly rise to free surfaces and disappear. Then surface treatments. First is natural or auto glaze, then applied or add-on glaze, then polishing and custom staining. So these are the methods of surface treatments. Then porcelain cooling. It is necessary to cool the mixture fairly quickly. If it cools too slowly, crystals form within the glass body, which will degrade its optical properties, turning it from a clear glass into a cloudy one. And that is also called as devitrification. If it is cooled too quickly, stresses build up in the glass. To reduce the stresses, it is kept near the glass transition temperature for a long time so that the atoms in this glass can rearrange just enough to relieve the stress. When most of the stresses has been eliminated, the finished glass is finally allowed to cool to the room temperature. Next is applications of powder or slurry system. These ceramics have great amount of translucency and highly aesthetic, used mainly as veneering layers on stronger cores and frameworks for making porcelain jacket crowns. Next is castable glass ceramics. Glass ceramics are polycrystalline materials developed for application by casting procedures using the lost wax technique, hence referred to as castable ceramics. Then castable glass ceramics. It is of three types: floor micas, apatite glass ceramics, other glass ceramics. In floor mica, dicor is the example. Then apatite for apatite glass ceramics, cerapper, and other glasses can be lithium based or calcium phosphate based. So this is the procedure. So first we make a wax pattern, then we sprue it, then we have this investing procedure. In this investment material, we pour investment material over the sprueing, and then we burn out. Then we do burnout, that is lost wax technique, and then centrifugal casting, then cast glass coping, and then ceramic. The ceramic oven, this is how it looks like. Then we have crystallized glass coping. Then we have conventional porcelain application and firing, and then this is how finished crown looks like. In mica based glass ceramic, we have dicor, developed by Corning workers and marketed by Dentsply International. The term dicor is a combination of manufacturer's name. Dicor is a castable polycrystalline fluoride containing tetrasilic mica glass ceramic material, initially cast by lost wax technique and subsequently heat treated, resulting in a controlled crystallization to produce a glass ceramic material. 55% volume of tetrasilic floor mica crystals. It increases strength and toughness, increases resistance to abrasion, and decreases translucency. Fabrication of castable ceramic restoration. First is casting. The glass liquefies at 1370 degrees Celsius to such a degree that it can be cast into a mold using lost wax technique and centrifugal casting procedures. The wax pattern of the proposed restoration made on the model or die is invested in castable ceramic investments in a double line casting ring and burned out in conventional burnout at 900 degrees Celsius for 30 minutes. Glass ingots of castable ceramic material is placed in a special zirconia crucible and centrifugally cast in an electronically controlled dicor casting machine, maintaining the spin pressure for up to 4 minutes and 30 seconds. Then transparent glass casting obtained is amorphous and fragile. Then ceramic. The cast glass material is subjected to a single step heat treatment called as ceramic to produce controlled crystallization by internal nucleation and crystal growth of microscopic plate like mica crystals within glass matrix. Then castable apatite glass ceramic, also available as cerapper. Apatite glass ceramic melts at 1460 degrees Celsius and flows like a molten glass, and when cast at 1510 degrees Celsius, it has an amorphous microstructure. Cerapearl is similar to natural enamel in composition, density, refractive index, and hardness. Then we have pressable ceramics. So it consists of two types: shrink-free ceramics or lucide reinforced glass ceramics. In shrink-free, we have examples: Restore, Alceram, and then lucide reinforced, we have IPS and press. Shrink-free ceramics. The shortcomings of the traditional ceramic-like failures related to poor functional strength and firing shrinkage, limited use of all ceramic for jacket crowns. The development of non-shrinking ceramics directed towards providing an alternative treatment. So if we have first generation IPS Empress, it contains 35 to 45 volume percent lucite as crystalline phase. Its disadvantage is the presence of about 9% porosity badly affects its fractional strength, limiting its use to single unit complete coverage restorations in anterior region. Then we have second generation IPS Empress 2. Contains 65% volume 65% by volume, lithium disilicate as main crystalline phase. Advantages: it has much higher flexural strength than that of IPS emprise, which makes it suitable for the usage of the for fabrication of 3-unit FPDs in the posterior region and can extend to the second premolar. Then we have properties of IPS Empress 1 and 2. Core ceramic, glass ceramic with 35% volume of lucite crystals. And in Empress 2, it has 65% volume lithium disilicate crystals. Lithium orthophosphate is much lower concentration. Then veneering ceramics also contain lucite crystals in glass matrix. Contains in IPS Empress 2, it contains apatite crystals which causes light scattering similar to that of tooth structure. Processing temperature for IPS Empress is 1180 degrees Celsius. For Empress 2, it is 920 degrees Celsius. Then we have third generation IPS Emax press. It was introduced in 2005. It is considered as an enhanced lithium disilicate pressed ceramic material when compared to Empress 2. Better physical properties and improved aesthetics. Then we have slip cast ceramics. It is also called as glass infiltrated ceramic. Infiltrated ceramics. It comes under the name Vita Inceram, supplied as one of the 3 core ceramics: Inceram Alumina, Inceram Spinel, Inceram Zirconia. In Inceram's alumina, it has 70% by volume alumina. Spinel contains a mixture of magnesia and alumina, and zirconia contains 34% by volume alumina and 33% by volume ceria stabilized zirconia. Definitions: a porous infrastructure is produced by slip casting, sintered and later infiltrated with the lanthanum-based glass, producing 2 interpenetrating continuous networks, one composed of a glassy phase and other with the crystalline infrastructure. Inceram alumina, 70% of by weight of alumina and 30% sodium lanthanum glass. Inceram spinel, mixture of magnesia and alumina. Inceram zirconia, 70% alumina and 30% zirconia. Now we're going to read about Inceram alumina. A slurry of aluminum oxide is applied on a refractory. The alumina core is then placed in furnace and sintered using program 1. Slow heating of approx 2 degrees Celsius per minute to 120 degrees Celsius to remove water. The second stage of sintering involves temperature rise of approximately 20 degrees Celsius per minute to 1100 degrees Celsius for 2 hours to produce approximation of particles with minimal shrinkage of alumina. So this is the fabrication technique. First we prepare dye, then mixing aluminous powder with water to produce slip. Then the slip is painted onto the dye with a brush, and then it goes for sintering. Lanthanum alumina silicate glass is used to fill the pores in the alumina core. The glass becomes molten and flows into the pores by capillary diffusion. Then removal of excess glass. Then veneering with aesthetic veneer. Then we have Inceram spinel, second generation material based on the Inceram technique. Technique for the fabrication is similar to that of Inceram alumina. The prime difference is it is a change in composition to produce a more translucent core. Then we have Inceram zirconia, that has zirconia and alumina used for posterior crowns and bridges, not indicated for anterior restoration due to its opacity. Then we have machinable ceramics, manually controlled systems or manually aided design or manual aided manufacturing methods. The best known manual system in the UK is Sille, referred to also as copy milling. Copy milling. In this technique, it is possible to mill a restoration from ceramic materials using special systems like Sille. Ceramic tube. The best known copy grinding system is Sille, which was introduced commercially in 1991. Sille was introduced by Dr. Stephen Edinburgh at the University of Zurich. A hand-operated contacting probe traces the external contour of an acrylic or wax inlay previously fabricated directly in the mouth. A milling arm following the probe by the means of pantographic arm with 180 degrees of freedom that cuts the copy of the pro inlay from a porcelain or glass ceramic block. The pro inlay is fabricated with a blue resin based composite made either directly on a prepared tooth or indirectly on the die made from the impression. The prototype is fixed into the Sillet unit at the surface of the pro inlay scan, and with the tracing tool, a coarse diamond coated disc simultaneously roughens out the shape of a ceramic restoration. A fine white powder is applied to the pro inlay and the scanning is done, again using the smooth disc and fissured and tapered parts. Matching fine diamond disc and burrs refine the shape of the gross restoration. Once the white powder has been completely traced off, the milling of the ceramic restoration is considered complete. Stains and glazes may be added to the inlay before etching and silicized. The time taken to mill the restoration depends on the experience of the operator, complexity of the restoration, and the sharpness of the cutting disc. The average time for milling is 20 to 30 minutes. Sillet manually added operator copper milling system use both feldspathic ceramics and aluminum dioxide material. Then we have CAD-CAM. It allows the dentist to make an optical impression of the tooth preparation and with the aid of a computer design and the restoration. The restoration is then milled from a block of ceramic material using a diamond wheel. The restoration is custom fitted to the patient's occlusion using diamond burrs. These are the pictures depicting the CAD-CAM technique. Then we have Ormosos. This is organically modified ceramics. So it represents a novel inorganic and organic copolymer formulation that allows the modification of its mechanical parameters. That's inorganic silicate network and organic methacrylate. The inorganic polycondensation and organic polymerization result in the formation of inorganic organic copolymer. Advantages: biocompatibility, reduced polymerization shrinkage, lasting aesthetics, and anti-kerogenic properties. Then we have ceromas. It is ceramic optimized polymer. It is the composite of specially developed conditioned fine particle ceramic fillers, which are closely packed and embedded in the advanced temperable organic polymer matrix. Uses for veneers, inlay, onlay without framework, and then can be used with fiber reinforced composite. The framework for inlays or only crowns and bridges, including implant restoration or metal framework. Then we have metal ceramic systems, cast metals, which consist of both noble metal alloys and base metal alloys. Noble metal alloys consist of gold, platinum, palladium, gold, palladium, silver, silver, then gold, palladium, palladium, silver, and high palladium. And base metal alloys, there's nickel, chromium, cobalt, chromium, free, and then other systems. Properties of dental porcelain are related to type of the interatomic bond, composition, and processing defects. Biological property: it is inert, that is tissue friendly, biocompatible. Solubility: it is indestructible in oral fluids. Only strong chemicals like hydrofluoric acid can dissolve dental porcelain. Dimensional changes during firing. A considerable amount of shrinkage and porosity occurs due to densification as a result of sintering, evaporation of excess water, and loss of binder. To decrease the shrinkage and porosity, following can be done: proper proportioning, oversize, proper compaction, use of small and large powder particles, and firing under vacuum. Mechanical properties: high compressive strength, high hardness. It is even harder than enamel, causing the wear of opposing natural teeth. Brittle, that is low tensile strength, low fracture toughness. So bulk thickness is required. It necessitates more tooth reduction. The strength is usually measured in terms of fractional strength, that is a combination of compressor, tensile, and shear strength. It is stiff material, high modulus elasticity. So limited elastic deformation can be tolerated before fracture. Optical properties: it is a translucent material. Basically, it comes in 3 shades: opaque, dentin, and enamel shades to recreate the color of the tooth. Once the exact tooth color is obtained, it is quite satisfactory and stable. Bonding to structure, it mainly depends on the type of the cement used and the surface treatment of the tooth and restoration. Then we have thermal properties. It is electrical and thermal insulator, and it has low alpha. Strengthening. So the methods of strengthening can be designing, depends on designing components, reducing the surface defects, interruption of the crack propagation, development of crystal compressive stresses within the surface of the material. First is designing the component of the restoration with no sharp line or point angles to reduce stress concentration, then reducing the surface defect. It can be reduced by use of powder with large and small particles, proper proportioning, proper compaction, proper drying, firing under the vacuum, slow cooling, and glazing. Interruption of the crack propagation can be done by two methods: crack deflection and crack healing. The first is dispersion of tough particles to absorb energy from the crack and deplete its driving force for propagation. For example, aluminum. Next, crystal structure changes under stress. The energy at the crack tip is absorbed to be used for phase transformation of zirconia from tetragonal to monoclinic structure. And this is accompanied by 6% volume expansion, and it will close the crack. So this is crack healing. Development of residual compressive stresses within the surface of the material. Ion exchange. It involves the forcing of the large potassium ion in the place of previously occupied smaller sodium ion, creating residual compressive stresses in the surface of the material during the chemical treatment. Next is thermal tempering. It involves the rapid cooling of the material while it is hot, producing a skin of rigid glass surrounding a molten core, which is going to solidify later. Then we have thermal compatibility. Ceramo-metallic restoration consists of metal coping and fired ceramic veneer. It is 3 times stronger than ceramic alone. Strengthening depends on the slight mismatch in the coefficient of thermal expansion and contraction between the metal and ceramic. That is, alpha of metal should be greater than alpha of ceramic. So this is how what they strengthen ceramic. So new ceramic materials and innovative ceramic processing techniques have been introduced in restorative dentistry since early 1980s. Some of these ceramics will share roots with the research that originated in Europe in 18th century. During the era of Nicolas Dubois de Chema, most advances are derived from the collaboration with the ceramics engineering community. Notable recent progress includes the advent of predictable ceramic materials and techniques for aesthetic complete crowns, partial coverage, and laminate veneer restorations, improved metal ceramic aesthetics with the advent of opalescent porcelains and framework modifications, introduction of CAD/CAM and machining as a route of fabrication of restorations, improved understanding of the clinical response of all ceramic processes and of material factors that influence clinical longevity. Strong scientific and collaborative foundations presently exist for continued development and improvement of ceramic systems by increasingly well-informed teams of resources and dentists. I hope you understood ceramics. Thank you.